Good afternoon and welcome to what is probably going to be the first of a few lectures on modular arithmetic. Modular arithmetic is at the heart of much of the number theory that we do in Olympiads, and many of us do find it difficult to get started because if you just do a Google search for modular arithmetic, you find stuff that are way too complicated for anyone to understand when they want to get started. And so hopefully this will be a useful way for us to build up our understanding in a systematic way. Now, of course, all of this is going to center around this statement. A is congruent to B mod n. What exactly does that entail? And how do I use it? And what sort of questions am I supposed to solve using modular arithmetic? So the first thing is to just know what does this actually mean. So symbolically, A is congruent to B mod n is just saying something very simple. Just means that A minus B is a multiple of n. So for example, we would be able to say that 7 is congruent to 4 mod 3 because 7 minus 4 is 3, which is a multiple of 3. I could also say that 17 is congruent to 5 mod 4 because their difference is 12, is a multiple of 4. So the first thing to know is that this is just a notation. Now, modular arithmetic is just a notation, and so there will be plenty of instances where you see a question says n is congruent to 1 mod 4. And you want to know what that means. You don't need to do anything too fancy just because it mentions that. So if I tell you that n is congruent to 1 mod 4, that means that n minus 1 is a multiple of 4. And that usually means roughly that n divided by 4 leaves a remainder of 1. Now this is not 100% accurate because n can also be negative, and so therefore describing it as a remainder is, well, accurate if we know n is positive, but otherwise not quite. So I could also say that 7 is congruent to negative 17 mod 6 because the difference is a multiple of 6. Now, this is notation. Intuitively, how you should view it is that each mod, some value, let's say if I just say mod m, divides the set of positive integers and negative integers. So just the whole set of integers into m clusters. Now, I'm using the word clusters. The technical term would be equivalence class. That's why I want to say but equivalence class is maybe a bit too technical, so we'll just say clusters. So if I'm working in the world of mod 5, that means I'm saying that, look, 1, 2, 3, 4 and 0 are the 5 remainders you can get when divided by 5. They are also kind of like the representative for 5 different categories of numbers, which one could really boringly write out as such. Notice that I've left some space above because we can also go backwards. And so on in both directions. So when I'm saying mod 5, I am dividing up my set of integers into 5 clusters. And whenever I say that things are congruent mod 5, I'm saying that they belong to the same cluster, which in the way I've drawn it means the same column. Right? So for example, if I now just looked at this and this, I could say that 4 is congruent to 19 mod 5. I could also say that those are congruent to -1. At the heart of modular arithmetic is the notion that in a particular problem or in a particular situations where I only care which cluster a number belongs to, will be when I can use mod whatever it is. So mod m, if I have 5 clusters like this and I want to know which of them it is, then mod 5. Now this means that of course different mods are doing different things, right? So if let's say that you have got mod 2, that's the just odd or even. So 0 mod 2 is even and 1 mod 2 is odd. Take note that when we say 0 mod 2, this is a short form for things that are congruent to 0 mod 2. So I could say that they are all chained together into a block of evens and a block of odds if I'm working mod 2. Now, mod 10, for instance, would be the last digit for positives. So for negatives, that would not be the case, but I could say, for example, 7, 17, 27, 37, all of these belong to the same thing, mod 10. However, it would be also congruent to -3, so that's where the last digit breaks down because you're landing in negatives. Okay, so now that we have sorted out what actually modular arithmetic is, we can then follow up by talking about how to use it. And many of you, if you are watching this and you have some familiarity with Olympiads, as early as in primary school, this modulo 10, the last digit, is something that we have often used. For instance, if I ask you for the last digit of 2023 times 2024, almost all of you instinctively know that I just need to care about 3 times 4 is 12, and so the last digit is 2, which you are absolutely right. Now, in modulo arithmetic terms, what this is saying is that you can make a one-to-one replacement, because I'm looking at mod 10. 2023 can be replaced by 3, and 2024 can be replaced by 4, because they are the same thing if all I care about is which cluster a number belongs to. And so when I have two things like this being multiplied together, it is also true that you can replace both of them with the simpler representative. This also therefore applies to mod something else. So if now I ask, well, I know the last digit, what about the remainder when 2023 times 2024 is divided by, let's say, I don't know, let's go with 19. Well, what I can do is that I can bring these down to something smaller. First, I'll divide by 19. This would give you 106, remainder 9. So that means that 2023 is congruent to 9 modulo 19. Now, of course, this would also mean that 2024, which is one bigger, is congruent to 10 modulo 19. And so the implication is that I can replace both of these with a smaller representative. Obviously, this is easy enough to calculate. And now 90, I can divide that by 19 again. Which, if you divide, you get 4 remainder 14. And so that will be your remainder. Now, this is going to be the easiest and most literal way to use modular arithmetic. So the second thing after you know the notation is that to get remainders when dividing by n, just reduce everything to a smaller counterpart mod n. This goes a long way beyond just multiplication, and the easiest way to showcase the power is using powers. Now, for instance, if let's say that I wanted to find the remainder when 2024 to the power of 2024 is divided by, let's use something like 9. Now, 2024, as many of you know, the divisibility test for 9 is the sum of digits. And so 2024, if you just use the divisibility test, it is 8 mod 9. So at first glance, this means that I can make a small improvement and say that 2024 is now congruent to 8 mod 9. So I can replace 2024 by 8, which is indeed correct. However, it is actually also true that I can replace 8 by -1. And this is the nice thing about modular arithmetic. You get to choose a representative that you like. Kind of like when Singapore goes to the Olympics. I would not be a very good swimmer, but Joseph Schooling would be a lot better as a swimmer, so he represents Singapore for swimming. But that does not mean he represents Singapore for everything else. You would probably not want Joseph Schooling to represent Singapore in every single sport. So in the world of mod 9, I can replace 2024 by 8, I can replace 8 by -1, and -1 is the best representative because -1 to the power of something is just, in this case, 1 because the power is even. Take note, however, that when we are replacing, what is happening is that I am replacing each number by its counterpart. I cannot replace this. This is the number of copies, and so you cannot replace the number of copies of something. If let's say that you go to a shop and everything is at 50% off, that means that the items are half price, not that half of the items have disappeared. So you change the price tag from $10 to $5, not you take away 5 of the 10 items. There are still 10 items if there were 10 items to begin with. So this is the nice feature of modular arithmetic. It allows you to be able to simplify quite a lot of things. Of course, modular arithmetic hinges on modulo what. So if I were to say 2024 to the power of 2024 is divided by 9, well, you can also divide it by other stuff. And modular arithmetic also explains why a few of these mods behave well enough that they give me divisibility tests. So they explain divisibility tests. Now, of course, you guys know the ones that are most famous, and I'm not going to add more tests, but we will understand from here why there aren't other tests. So we know that for 3 and 9, the test is for the digit sum. And some of you may know this test for a long time and may not actually know why it works. Well, the reason why no one has explained it to you is because it requires modular arithmetic, which, as you have seen, if we start from the very beginning, it has already taken us 15 minutes just to say what it is and the basics of how it works. And if you are a primary 3 student, I don't think you have the patience to listen to all of this. So the digit sum, how does it work? If we just consider a number, like let's say, what's a good number? Every time I ask that in class, someone gives me 1, 2, 3, 4, 5, 6. So I cannot object to that. Let's use 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Supposing that I wanted to divide it by 9, that means that I want to figure out what does it become mod 9. Now to do that, I'm going to write everything down in terms of place values. This is of course something that in our first understanding of big numbers, we know that each place value is the thousands place, 10,000s place, 100,000s place. I can also write them as powers of 10. Now the magic happens because 10 is congruent to 1 mod 9, because 10 is 9 more than 1. So I can replace all the 10s by 1s. And this is great because, as we all know, powers of 1 are still 1. And this is our very ubiquitous divisibility test. Now, this is true also for 3 because 10 is also congruent to 1 mod 3. So in our case here, this is 21, which is congruent to 3 mod 9, or if you wanted to say 0 mod 3 as well. More simply, this also explains why for powers of 2 and 5, you would just look at the last n digits if it is the nth power of 2 or 5. Because essentially, 10 to the power of n or more will be 0 mod 2 to the n and 5 to the n. When we say something is 0 mod something, it means that it's a multiple of it. So 10 to the power of n is a multiple of 2 to the n. So if, for example, I were doing mod 8, which is 2 cubed, this and this would all become 0, and therefore I only need to focus on the last 3 digits, which is the test for 2 cubed equals to 8. Now the last test that many of you are aware of is the test for 11, which is the alternating sum from right to left. The alternating sum from right to left, meaning that, for example, now if let's go with a different number, let's go with, because I'm really boring, let's go 6, 5, 4, 3, 2, 1 instead. Now if I've got 6, 5, 4, 3, 2, 1, and I want to get the remainder when divided by 11, I can use the same idea as before. basically saying that mod 11, 10 is congruent to negative 1. And therefore, if you were to just write this down, you get minus 6 plus 5 minus 4 plus 3 minus 2 plus 1. This is what the alternating sum means. And right to left, because the final one is plus. This would give you negative 3, which if I'm asking for remainder, you just add back 11 and you get 8 mod 11. Now this would tell us why we do not actually have divisibility tests for, let's say, something like 7, because 10 is just congruent to 3 mod 7, and I'm sure that we would not consider that as a very big improvement. However, we are able to extend our understanding of divisibility test using modular arithmetic to sometimes handle other numbers. So for example, if now I had modulo 101. Now if I'm working with modulo 101, I can use the fact that 100 is congruent to negative 1 mod 101. And so if, let's say, I had 654321, do we have a divisibility test for 101? The answer is yes, we do. You may not have known it previously, but now we can generate it on the spot, which is that if I slice them into 2-digit blocks instead of 1 digit at a time, you can write them in blocks that are multiplied by a power of 100 and replace these by negative 1. So it is now like the test for 11, except that you take this in 2-digit blocks rather than 1. So this is 43 modulo 101. Oops, it went off the bottom of the screen, right? Apologies for that. So to this point, our understanding is that our modular arithmetic justifies as well as can provide us with these divisibility tests. However, there is, of course, a limit to how much our divisibility tests can do. Not every number would have something like this. And also, you don't always want to have very large mods. And so another thing that we can do with mods is that you can split and you can recombine. Now you can split and recombine modulo information, which now I am referring to as information, because you can think of it as each modulo is giving you a view of the number, like a front view and a back view and a side view. They're all giving you part of the picture. Now if you combine more of them, you get more of the picture. So for instance, if let's say that I told you that n is congruent to 1 mod 6. Maybe that's boring. Let's go with 5 mod 6. Now n is congruent to 5 mod 6, meaning that when I divide by 6, the remainder is 5. Now 6 is equal to 2 times 3, which means that you should be able to then say that what is n congruent to mod 2 and mod 3? Well, if n is congruent to 5 mod 6, that means that it is also congruent to 5 mod 2, which you reduce to 1 mod 2. It is also congruent to 5, which is 2 mod 3. And so you have essentially split 5 mod 6 into 1 mod 2 and 2 mod 3. This is the splitting. It is quite obvious that we should be able to split up the information. However, what is also nice is that we can recombine the information together. If let's say that I'm looking for a number that is 2 mod 3 and 1 mod 2, then I can list out one of them until it satisfies the other one. So 2 is 2 mod 3. That's not 1 mod 2. The next thing that's 2 mod 3 is you add 3, you get 5. Now, is 5 also 1 mod 2? Yes. And so the number 5 satisfies both of this. And if I have got 1 mod 2 and 2 mod 3, in order to continue satisfying it, I can increase it by their LCM. Which of course, the lowest common multiple of 2 and 3 is 6. As we are looking at this, understand that this can also be generalized beyond small numbers like this. If let's say that now I just concocted something random like n is 7 mod 11 and n is congruent to 12 mod 17. Now I claim that I can recombine them, and it is guaranteed that I can, as long as these have no common factor, i.e. they are co-prime. It means that you can combine them uniquely. When I say uniquely, it means that n would be congruent to something modulo their product, which is 187. This statement here is what is known as the Chinese remainder theorem. The fact that you can is the Chinese remainder theorem. How you actually combine them is not described by the Chinese remainder theorem. That's for you to do. And how one would do it in the most just boring but straightforward way is to just again list out the things that are 12 mod 17 until it satisfies the other one. So 12 mod 11 is 1, so that's not going to work. If I add 17, however, this is now going to already work. Okay, I did not expect it to work that quickly, but that is good. If you feel that, okay, this is a bit too cheap because that's so obvious, let's change this to 13 mod 17. So 13 is 2. Now if I add 17, 30 is now 8 mod 11. And if I add again, this is now 3 mod 11. If I add it again, this is now 9 mod 11, and you feel that, is it really going to work eventually? Well, the answer is yes. But I may not want to list it all the way there. So I see that I've got 8 and I've got 9. Where am I going to ever get 7? Here. So I can always just make it happen by subtracting into negative land again. And so it turns out that here n would be negative 4 mod 187. which is also a valid way to describe it. It would be the same as 183 if you have a phobia of negative numbers. As a result of this, we are now able to combine. Therefore, I'm not afraid to separate things out. So for instance, if I now ask the question of what are the last two digits of 2024 to the power of 2024. This is just mod 100, and I can split it up into co-prime things. So I cannot say mod 10 and mod 10, because if I ask you for the last digit 2 times, that definitely does not give me the last 2 digits. So you split it up into 4 and 25. In other words, I'm going to get the information of what is this mod 4 and what is this mod 25. Now it turns out that both of these are easy to answer because 2024 is a multiple of 4. So it will be 0 mod 4, and 2024 is congruent to negative 1. So it would be just 1 mod 25. So I have 0 mod 4 and 1 mod 25, and then I can put it back together again, as mentioned, just by listing out the things that are 1 mod 25 until I get something that is 0 mod 4. So the last 2 digits of this would be 76. At this point, this means that we have the ability to calculate most of these things. As one final example, let's say that I now ask what is the remainder when, let's go with 101 to the power of 102 is divided by, let's go with 42. Remember that, of course, I can reduce the number 101. 101 divided by 42 is 2 remainder 17. But I cannot reduce this any further, so instead I can reduce down the 42 into 6 and 7. I could also reduce it into 2 times 3 times 7, or 2 times 21, or 14 times 3, but the reason why I split it into this is I want all the numbers to be small, but 6 is small enough since, like we have seen a couple of times, I can use the trick that 17 is congruent to negative 1 mod 6. So I already have one of these, and how do I get the one for 7? 17 reduces to 3. If we don't see a simple way to reduce it any further by, let's say, changing it to a smaller representative, then what we will do instead is to find a pattern. This is how it goes. I want to see the pattern of powers of 3 mod 7, so 3, then 3 squared is actually just 2 mod 7, and each time you just now multiply the previous one by 3 and then simplify it down mod 7. So 18 becomes 4 times 3 is 12, that becomes 5, times 3 is 15, that becomes 1. And once you have seen 1, you know that it will loop back again. Therefore, 3 to the power 102, if it repeats with a period length 6, you divide and you get a remainder of 0, which means that it occurs at the end of the period. It's just 1. No need to have much headache in combining them therefore, because 1 mod 6 and 1 mod 7, obviously the number that satisfies both of them is 1. Now, at this point, the question would then arise of, okay, you have just found this pattern down here. What happens if the pattern does not actually show up? There's no pattern. Or what happens if the pattern takes far too long to discover? Well, we will leave that for the next video, where I will talk about the few famous modular arithmetic theorems, which are our Fermat's little theorem, Euler's theorem, Wilson's theorem, and things like that, which will allow us to have further shortcuts in doing these sorts of calculations. But for now, this is Modular Arithmetic 101. I hope this clears up any questions on how basic modular arithmetic works, and then we will top up slightly more advanced things in the next video. So thanks for watching, and see you again on the next one.